We have Fady, Eskandar, Tariq, and we have Imad. We are here to present our project, which is multi-manual object manipulation using fully actuated Hexarotors. Okay, so okay, sorry, it works with this. Okay, so basically, our mission here is to move, as in control a box from one place to another using two Hexarotors on each side of the box. So basically, for our work, we are using a fully actuated Hexarotor, which is a Hexarotor whose rotors has been tilted by about 47 degrees. So this allows the Hexarotor to move with 6 degrees of freedom instead of it being constrained. So it can move in the whole picture and also in the XYZ. This allows for full movement. We have the different joints in the Hexarotors. We have the base joint. We have the base link, which is basically the frame at the center of the Hexarotor itself. Then we have the base footprint, which is basically at the bottom of the Hexarotor, which is just for the Isaac link. Then each of these rotor joints represent each of the 6 Hexarotors in each of the 6 rotors in the Hexarotor. And then we have the arm joint, which is basically the end effector here, that basically connects and carries what we want it to carry. Now, also for the box, we generated a box in Isaac Sim, basically by uploading a TRDF, and we attach sensors to all 6 parts of the box. This is to calculate the force feedback on the box, the force feedback that the Hexarotors are placing on the box for proper measurement. All of this was carried out in Isaac Sim 5.1 using ROS2 Jazzy. We basically used different extensions. We use an extension for each of the 2 Hexarotors. This is the controller for the first Hexarotor and the one for the second. We use this during the tuning of the system, and also we used it to monitor the different wrenches on the box. Now, so this is Tariq to continue with the work.
So in order to control these 2 Hexarotors, we have 2 types of PD geometric controllers. So the first one will be on R3 only, that's the translation one. So we must figure out what is the error, and this is a convention, this is an opposite convention of what we used to do in the lecture. We set the desired position, the X, Y, and Z, as the positive one minus the current position. Okay, so in the controller equation, in order to compute the forces in X, Y, and Z, we multiply this error by only Kb, not negative Kb as the lecture. And the velocity itself, the velocity will be the derivative of that error. So that will be the current velocity minus the desired one, and the desired one is 0. So it will be that's the opposite here. The desired one, which is 0, minus the current one. So this minus will be here beside the Kd, and the Kp is the proportional gain, and the Kd is a damping one. This is toughness and this damping. So from the other perspective of SO3 to control the orientation of the Hexarotor, this will be the equation for the error in the rotation. Half of our desired transpose, the rotation desired transpose multiplied by the current one, minus the current one transpose multiplied by the desired one, and all of that will be skew symmetrized. Instead of being just the 3 values, that will be a skew symmetric matrix. And also for the angular velocity error, that will be the dot of this, and this is calculated as the current one minus the desired angular velocity. So, and this will be the equation for the torques and the 3 as a 3 value. But this is in the body frame. So this torque is a desired torque in the body frame, and this was the desired force in the whirled frame. So in order to compute the wrenches in the wrenches desired in the body frame, we have to compute first the forces in the body frame. So the forces in the body frame will be the forces in the whirled frame multiplied by the rotation, the current rotation of the Hexarotor transpose. Okay. So now we have this wrench, this desired wrench, but we cannot apply this desired wrench exactly like this. If you consider this only, so we are considering the Hexarotor like a satellite or just a body in a space without gravity. So we should additionally add this wrench due to gravity. in the body frame. And this will be explained by Fady in the challenges, because we have a problem at first by how, in which step we should add this range exactly. So now let's implement it aside from the mathematics. So the mirroring. We have two hexarotors. They are not pointing like this. They should be pointing like this. So if you assign a message, like in the positive x, if we want this hexarotor to move in the positive x, in the world, the positive x like this. The first one will move in the positive x, but the other one will move in the positive x like this. So this is not preferred. We want both of them to converge instead of moving with each other. So we have to mirror that x. What about the y? They should move together. What about the z? They should move together. What about RPY? So this is the point from this picture, that we actually have a mirror, but maybe not mirroring like this, and this mirror is correctly mirroring. So let's begin by the trajectory to figure that out. The first trajectory is just RPY, the roll pitch yield test. So in this trajectory, we're implementing the limits, we're hitting the limits of rolling and pitching and yaw. In order to figure out, okay, if we are mirroring, so that the x will be in a body frame, will be defined in a body, because this positive x is different than this positive x. And the y is the same, the z is the same. What about the roll and pitch and yaw? What will be the difference? So now, this is a plot for RPY, for Hexarotor 1 and Hexarotor 2. This solid lines is the current angle of the Hexarotor, but the dashed lines is the target. So you will see that the target is the same for both. The target is the same wave. But the difference will be in the solid lines. The roll part, or the red part, this is the roll. So both of them rolling with the same. If I put a message like 45 degrees for the roll, so both of them will roll in the same direction. Okay? The yaw is the same as well, but the difference is in the pitch. So this is positive like this, but this is shifted. So the pitching, actually, if you are pitching with positive, they should be like this. But if you see from the world, so both will be like this, will be like this for the angle from the world perspective. So we inverted that, and this is explicitly here and defined in this figure. This figure, actually, it's not important right now, but let me explain it because we will use it later. This figure is actually compared between the grounded truth range that's exerted by the hexarotor, which is defined by these dashed lines, and the ones that will be just like something like feedback, the ones sensed by the box, okay, and that will be the solid lines. And these six figures, because we have 6 sensors, one in the positive of the box, positive x in the box, one in the negative, and the same for y and the same for z. Okay, so this is the first trajectory. The second one, we implemented just changing the z. Okay, and this is defined changing the z like this in the position figures. And you might figure that there is a little fluctuation in the pitching, but this is due to just the error. The fluctuation is between 0 and -4, so this is very small. And this is inverted here because we said already that both of them will be different in the body frame. The third trajectory is drawing a circle. So we are drawing a circle in the y-z plane. So the only changing here is the y and the z, the green and blue. Okay, but the red, the x is the same. Okay, so this is the circle. Then we plotted a square, but the square will be on another plane in order to show that we have a robust movement. So this will be in the x-z plane. So the only changing is the x in red and z here. But let me figure something out. We have the desired wave of the x is a dashed red. Here and here is the same. But what about the solid one? The solid is offset a bit. So in the Hexarotor 2, it's just the same. But in Hexarotor 1, there's an offset. Why is that? Because initially, when we are defining the Hexarotors, the first one will be in the 0, but the second one will be on 4. We should have a distance between them in order to hold the box. So this is the offset. So actually, if we publish a message for the x, that will be here +0, but here plus offset. Okay. Then this is just to show off. This is a star in the YZ plane as well. So this is just drawing 10 vertices star. So the only changing is y and z here and here. Then the last one, that will be back in place. We spawned a box, right here. So we're just holding that box with appropriate force in the positive x direction. Then we carry that box to a location. Then we bring it back to the home position. So you can figure out that here we are applying the force in the x direction. So we are concerned about only these two blocks. Okay? You cannot differentiate between the solid lines and the dashed lines in these plots. Why? Because actually we are applying the wrench with the Hexarotor in a horizontal direction. So all the wrench will be reflected will be sensed by the box. So both of them are actually on the same line. If there is a difference, so that will be reflected in Isaac's end. Because if we imagine if we are applying the forces, but in this direction, the Hexarotor is pointing downward or upward. So the actual sensed one will be just the horizontal component. So there will be some force subtracted from the one originally applied. But here, alhamdulillah, we didn't have that problem here. Then Muhammad Ahmed will continue with the last architecture.
For the rest of the architecture, this is our overall architecture graph. We have five nodes. Each node has a number of topics. The first one is the Hexarotor Bose Distributor GUI. This is our GUI that we use to run the desired pose or to give the commands. It has a number of topics. One is the Hexarotor target pose, and the second is Hexarotor 2 target pose. This one we publishes, they are topics that we use to publish the desired pose that we want to give to the Hexarotor 1 and Hexarotor 2. It also sends the same topic to the Hexarotor current pose plotter in order to compare between the desired and the actual pose. Okay. This one is only we use to activate the trace, and this one is the real one that publishes the trace of the Hexarotors, and we can control the time of the trace. We can make it 1, 2, or 3 seconds or more. Isaac Hexarotor 2 and 1, they are the nodes that takes the pose from the GUI to the Hexarotors in Isaac's sim. So Isaac Hexarotor 2 target receiver, it takes the pose that we get from the GUI, and it publishes 3 topics. One, the current pose, the real current pose that Hexarotor goes to, and the current roll pitch and yaw, and Hexarotor ground truth range. This is the real range that comes from the Hexarotor on the box. Okay. For the third one, Isaac Hexarotor 1 target receiver, it also does the same. Hexarotor current pose, this is the current position of the current pose of the Hexarotor, the current roll pitch and yaw of the Hexarotor, and the ground truth range. And the fourth one is the box range sensor. Here we didn't put 2 sensors on 2 faces. We put 6 sensors on each face. They measure the real range that comes out of the Hexarotors that's applied on the box itself. Okay. And Hexarotor current pose. This node is responsible to put the plots that Tarek showed before. Okay. Now for the challenges.
Okay, so every project comes with its own set of challenges. So one of the things that we faced early on was the implementation of the gravity. So we first modeled the gravity in the body frame rather than the world frame, which caused the controller to go haywire because it didn't know where the gravity actually is. Because whenever the drone rotates, it assumes that the gravity rotates with it. So it didn't make any sense, and we couldn't control the drone. We figured that out very fast early on. The second challenge was we first implemented the controller to be on R3 only. As you can see that the drones are a bit shaky. They can maintain their own pose, their own location. I'm sorry, but for the angle, for the orientation, it was very smooth or soft. Another problem we face is that when we eventually implemented SO3, we had a problem with our allocation matrix. And we had to go back to MATLAB and check what we did wrong back there, and because we implemented it wrong, we couldn't actually implement SO3 correctly. Also, at first, when we were controlling the drones, we were using manual control without ROS. So basically, we had the two GUIs that was mentioned before, and we were controlling each XYZ for the first drone and the second drone manually. Of course, we tried lifting the box that way, but it didn't go as planned. Because in order to lift the box, both have to move simultaneously. So simultaneous motion had to be made through a ROS node rather than just doing it manually. This is the ROS GUI that we developed. Basically, the trajectories that Tariq mentioned before could be just, you could just manually select which trajectory you want to implement, and then you can implement it. Also, you can control the XYZ manually here. And you can stop and start the trajectories in the middle of the simulation. So it was just very easy to work around the simulation itself. Of course, initially these were mistakes. Now for the tuning part, we had many problems starting with the lifting of the box. First of all, when we started lifting the box, because we are applying a force that is misaligned at the center of mass, so it applied a torque on the drone itself, which caused the drones to both pitch down, which made the lifting effect very difficult. So our first solution was to add a plate, a pressure plate. It was invisible, so that's why you couldn't see it in the simulation, to better distribute the pressure so that we can actually grip the box better. After even adding the box, it still slipped, the rotors were still misaligned, so we increased this box surface roughness, increased the force through making the ZX point at the center of the box. If the box isn't there, both end effectors will touch. What does that mean actually? So both drones don't actually see the box. All they want to do is actually to hit one another. That was the whole control idea. So that they can apply maximum force and maximum contact with the box. Is that the best implementation ever? Not really, and we'll see why later on. Yeah, this is this is the negative pitching point that I mentioned earlier. But this one, when you're actually moving the box during the trajectory, the box actually kept tilting. Yeah, we adjusted the gains of the omegas of the pitching and the rolling so that we resisted this pitching motion. Lastly, what happens if during the trajectory the box falls? Well, because of the earlier solution we made, the drones would automatically go very fast, and actually crash into each other. So instead, we moved the desired point to be actually a bit further away, so that the drones don't want to actually touch each other at the center of the box, but rather than still inside the box, but a bit further. And we increase the KP in the X direction to generate more force so that we can still maintain the gripping force. These are the tune parameters that we settled on after trying different gains and seeing how that affects our trajectory and goals. And this is a trial before the tuning itself. As you can see, the drones would be very sloppy. They would be pitching down. They won't actually be able to lift the box, and probably the box will fall during the second or third drone. So first of all, we can see there is very high pitching. We adjusted that by increasing the stiffness or the KP in that pitching direction. Okay, so preset. Okay, so now for the finale. So were we were able to manage to do it? Were we able to lift the box? How good was it? Let's see here. So this is of course a sped up simulation. It's 16 times the normal pace. We're here just trying to showcase that it's not only able to do it once, but it can do it for, I think it ran for almost 30 minutes until we got bored and then stopped. So yeah, and it's very robust. The key point is that the drones were able to exactly put the box back into its original place. And even if there was slight misalignments because of the higher stiffness in the yawing, they were able to actually align themselves correctly with the box without making the box fall or without the box fall. Okay, so this was our original target that we were just going to finish to build the box, but yeah, we kept thinking, how robust is it actually? What can we do more? So actually, Tariq came up with the idea that the four of us, T, F, T, F, M, F. So we could just maybe lift the box and then draw an X, basically. So change. As you can see, we can change the position in the Y direction, the X direction very fast, very steep. But still, the drones kept contact with the box very well, and actually were able to drop it at its desired location and continue the trajectory on its own.
This could be the name of your company.
Yeah, exactly. So one last thing, actually the project was uploaded to GitHub. You can basically just click on the link and you'll find the GitHub. You'll find the GitHub repo with everything that we've done. We'll also find a README file where I can show you how you can run the simulation, how to run the simulation, see what we did exactly, all the required downloads that you need to do. So basically, a full documentation of our work, and yeah. So tag us or cite us if you use it. One last thing. This is the making of the project. These were 2 consecutive days actually. Finished at 2 a.m., 4 a.m., 4:30 a.m. And we had to showcase that, and we were actually very dedicated. Thank you all.